Hi students, today I am going to tell you about WaveMotion. Now what exactly are waves? We keep hearing about light waves, radio waves, sound waves. So how is wave motion different from say a ball moving on the ground? There is a key difference. Wave motion is the method of energy transfer from one point to another without bulk transfer of matter. What this means is that in wave motion, energy moves from one point to another, but matter does not move from one point to another. So if I am making a sound, the sound energy is moving from my mouth to your ear, but the air particles, near my mouth, they are not moving, from my mouth to your ear. Only energy gets transferred, matter doesn't get transferred in wave motion. Here's another example. In this pond, when a pebble is dropped, the energy that the pebble imparts to the pond, that's what gets transferred from the center of these circles to the periphery radially. But the water itself does not move from the center to the periphery. It's the energy that moves because of the vibrating particles of water. The particle here vibrates, the particle here vibrates, the particle here vibrates, the particle here vibrates, but all these particles are not actually moving from the center of the circle to the periphery. They're just vibrating, and the disturbance, the vibration, is what is moving. It's moving like this. If you look at this leaf here, it does not move radially. Had the water moved radially, this leaf would have moved too. But this leaf just bobs up and down because the particles vibrate, they don't move radially. Take a look at this loudspeaker, for example. Again, energy is transferred from the loudspeaker to your ear, but the air particles are not transferred. It is the energy that travels in the shape of a wave. There are two types of waves. The first type of waves are electromagnetic or non-mechanical waves. These are waves which do not require a medium to travel. This means that energy can be transferred from one point to another point in this kind of wave motion without there being any vibrating particles in between. Sound waves are not electromagnetic waves, for example, because they require air, but electromagnetic waves can travel through space also because they don't require any medium. Light waves, radio waves, infrared waves are all electromagnetic waves. So you receive heat from the sun, which is thousands of kilometers away. Even though there's outer space in between the sun and you, there's no air, but because electromagnetic waves can travel through space, you feel hot. The next type of waves is mechanical waves. In fact, these are the types of waves which we are going to focus on in this chapter. Mechanical waves require a medium to travel. So for example, when I make a sound from my mouth, the air particles near my mouth start vibrating. This causes the next air particle to vibrate. This causes the next air particle to vibrate, and so on, So the medium particles vibrate, and because of this, the sound energy is transferred from my mouth to your ear. The disturbance in case of mechanical waves propagates through periodic motion of medium particles about a mean position. So the medium particles vibrate, and this causes the disturbance to be transferred. So here you can see there's an energy source. This energy source causes the particles of the medium to vibrate, and this transfers the energy from particle to particle. Mechanical waves are of two types: transverse mechanical waves and longitudinal mechanical waves. The difference between them is simple. In case of transverse mechanical waves, the medium particles vibrate perpendicular to the direction of motion of the energy. So if energy is being transferred, from left to right, in case of transverse mechanical waves, the particles move up and down like this. So here you can see one of the particles moving, but actually all the particles along this wave are moving up and down, up and down. In fact, if you took a snapshot of all these moving particles and saw the picture, this is what you would see. You would see that all the particles are moving up and down and vibrating in such a way that if you join all the particles at any instant, the shape you will get will be the shape of a wave. Isn't that interesting? Here's another example. If you look at this particle at the end of this wave pulse, you can see that it vibrates up and down as the wave moves on from left to right. We've shown just one particle vibrating in this case, up and down, but a lot of particles vibrate like this, up and down, and that's what gives the impression that something is actually moving from left to right. The disturbance is propagating from left to right. Have a look at some examples of transverse waves. A vibrating string is one example. If you pull at one end of a vibrating string, the disturbance gets transferred to the other end by means of the string particles moving up and down, up and down. Similarly, an audience wave. In Mexico, what happens is sometimes thousands of spectators stand and sit, stand and sit, stand and sit. They do this again and again. They just stand up and then they sit down, and they do that alternately, like one row stands up, then another row stands up, then another row stands up, and then the first row people sit down. Now all this causes, if you look at this event from a distance, you'll feel that a wave is passing through the audience. So this is exactly how a transverse wave works. People are just standing up and sitting down. They are not moving from one place to another, but the energy, the disturbance is being propagated through the audience. So that's also an example of a transverse wave. Now we come to the second kind of waves, longitudinal waves. Longitudinal waves are very similar to transverse waves, because in this case also particles are vibrating and energy is being propagated. But in this case, the particles vibrate from left to right if the wave is moving from left to right. In longitudinal waves, the particles vibrate in the same direction in which energy is being transferred.